Thanks, Abhishek, and thanks to Subhro and Sergej for organizing this uh, exciting workshop and inviting me here to talk about this work that I've been doing for the last 2 years. So I'm going to talk about non-invertible symmetries and some lattice models that have these symmetries. Yeah, and this based on this work that I've done with Shuheng, Nat, and Jimmy in these papers. Okay, so I don't have to sell generalized symmetries to this audience, like we all know what they are. The modern perspective is that these are topological operators or defects in quantum field theory setting. This could be like higher form symmetries or non-invertible symmetries or more exotic symmetries. But in the last few years, this was a development that started in continuum field theory, but in the last few years, people started to understand and realize this on a lattice, in particular in a quantum Hamiltonian on a tensor product Hilbert space. And the simplest example of this is the Kramer-Swannier duality in 1+1D transverse field Lie model. So let's quickly take a look at that. The setup is as follows. You have a 1D periodic chain with qubits on every side. And the Hamiltonian is well known. You have a Ising term, like a nearest neighbor interaction, and the transverse field term. And it has some standard symmetries. There's a Z2 spin flip symmetry that flips all the spins on all the sides. And that's generated by this product of X. And it also has translation symmetry. And this model was solved exactly by Onsager very long ago in the 40s, at least a classical version, but you can say the same thing with the Hamiltonian. And we know the phase diagram. So the Z2 symmetry is spontaneously broken for small h, and it's preserved at large h. These are some representative ground states in these phases. And there is a transition at h equal to 1, the second order transition is described by Ising CFT. But I want you to focus on this value being exactly 1. This was in fact known even before Onsager solved this. Kramers and Wannier pointed out that there is a duality in this model. In the Hamiltonian language, this corresponds to exchanging the x and zz term. And under this exchange, h goes to 1 over h, so which exchanges these two phases. So for generic values of h, this is not a symmetry, but at h equal to 1, where the model is self-here, there is a symmetry. Now we learn in textbooks that symmetries are usually implemented by unitary operators. So let's try what happens in this case. So let's say there is a unitary operator that implements this transformation and see how it acts on the Z2 symmetry. And recall that the Z2 symmetry is generated by product of X. And as I said, showed here, X is mapped to ZZ, but that product is 1. This is a contradiction. This is totally fine on Z2 even states, but this doesn't make sense on Z2 odd states. This is the first indication that this cannot be implemented by a unitary operator, and that's why it's a non-invertible symmetry, which was analyzed in the continuum like some decades ago and on the lattice in the last decade or so. And today I want to look at the like the quantum version of the quantum Hamiltonian version of it. So this was studied in the last couple of years by Nati, Shuheng, and Sahan. Here's an expression that they wrote down. So the stuff in pink here is product of unitary operators. And it has this nice sequential quantum circuit picture where you apply local unitaries on consequent sites. And finally, there is this projection onto the Z2 even sector. And that's what makes it non-invertible. If not for this, it would have been like a unitary invertible thing. You can also compute its algebra. It implements the Kramer-Swannier duality as we want. And it satisfies these fusion rules. Is exactly what you see in the continuum, except for this extra factor of translation here. That's some new feature on the lattice. But other than that, it's like the standard Kramer-Swannier duality in the continuum. Now, yes. Yeah, it's just chosen so that I don't get any weird factors here. On the lattice, I don't know how to motivate it, but in the continuum, there is a well-defined way of fixing this normalization. Basically, you want the defect Hilbert space to have like an integer dimension. And to make that consistent, you have to choose this normalization. Yeah. So what I want to point out is some issues with this representation. This is nice and cool, but it's not manifestly translationally invariant, right? Like you have this ladders, like a staircase kind of structure that's not manifestly translationally invariant. So it's not clear how to derive this. Like you can show this, takes a lot of work. And even to derive this fusion rule, I invite you to do it, or rather challenge you to do it in this representation. It's quite tedious. The way people, at least these people showed it, is by doing a Jordan-Wigner transformation, going to a Majorana picture, and then it simplifies quite a bit. But if your aim is to generalize these kind of symmetries to higher dimensions or other models where you don't have this Majorana picture, then you need some other representation, which is more convenient. And that's where the tensor network representation comes in. So in particular, it's a matrix product. You can write it as a matrix product operator in this form. I'll explain what this diagram means soon. But one thing you can already notice looking at it is that it's manifestly translationally invariant. There is this motif in the square box that's repeated periodically in the spatial direction. So translation invariance is manifest. And as I will demonstrate in this talk, you can also easily generalize this to other models in higher dimensions or even beyond Euclidean lattices on LDPC codes, on graphs and all that, if time permits. And all of this is possible because of a nice graphical language called ZX calculus, which was invented by, developed by quantum information community to analyze like linear maps between qubits. It's really powerful, and I just want to give you a teaser of how it works. So here's the quantum teleportation circuit transcribed into a ZX diagram. And you can use ZX calculus to verify that this does implement quantum teleportation. And it works this way. We are left with this diagram. This is teleportation. You just copy a state, take the state from Alice and send it to Bob. And so that's what I'm going to talk about first, lightning review of how ZX calculus works, and then use that to construct these non-invertible symmetries in 1 + 1D, 3 + 1D, and beyond. And then finally, I'll discuss some actual physics where I use these duality symmetries to constrain the low energy. Any questions at this point? Yes, I'll mention that in the end, but yeah, there is a generalization of ZX calculus to ZM. Yeah. So let me talk about ZX calculus. As I said, ZX calculus is basically is all about representing linear maps between qubits as diagrams. So that's called a ZX diagram. And these diagrams are built out of some set of generators. Here are some three fundamental generators. The first one is called the Z spider. It looks like a spider, and that's why it's called a Z spider. It has N inputs and M outputs. And it has a phase alpha inside the spider. That alpha shows up in the second term here. So it's defined as this operator. And the X spider is defined similarly, but now the 0 and 1 are replaced by plus and minus. And then there's the Hadamard gate. That's presented by a yellow box. Here are some examples of familiar operators as ZX diagrams. So you take the green spider with a phase pi and one input and one output that corresponds to the poly Z operator. You can also construct its eigenstates using the red spiders. And it's customary or convention to omit the phase when it's multiple of 2 pi, like 0 or 2 pi or whatever. And you can also construct the poly X and its eigenstates in this way. And the GHZ state, for example, slightly more non-trivial example is GHZ state, which is given by this green spider with 3 output legs. Now, this is some useful mnemonic. Like if you ever forget which one is a green, which one is a red one, this is a useful way to remember it. The GHZ state is given by the green spider. There's a bunch of other generators, simpler than the ones I showed before. There's the identity, which is just a single wire. There's a swap, which is two wires that just go through each other. And then there's a bell pair, the Ket version and the Brower version of that. And these generators can be combined to construct a more non-trivial operators. For example, here's a ZX diagram for a C0 gate. So on the left of the red dashed line here, I have 2 generators, one spider with 3 legs and one identity generator. On the right, I have again 2 generators. What I'm doing here is taking a tensor product of this with the identity and the tensor product of this with this, and then gluing these wires together. So when I place diagrams next to each other, that's like tensor product. When I glue those wires, it's like a product or composition. And in this case, you can evaluate this matrix and it turns out to be the C0 gate. And what makes working with ZX calculus very powerful is this very nice property that you can deform the interior of this diagram arbitrarily as long as you keep the inputs and outputs fixed without changing the linear map that it represents. So for example, this is how I constructed C0 in the last slide. You could as well construct it in this way. And you can check this manually that these two represent the same diagram. And it's customary to write it in this way. Whenever it's ambiguous, you can deform it any way you want, and you'll get the linear map you want. This goes under this slogan, only topology matters. But then you could ask, like, what about topologically inequivalent diagrams? Like if I just give you two ZX diagrams, are they the same linear map or not? And in fact, there are relations between the generators. They're not all independent. For example, if I take this green spider, empty green spider with two legs, that's the same as the identity operator. Or a more familiar example is this Hadamard. If you take two Hadamards, h square is 1. So that's another relation. So you could ask, like, how do we know, like, how many relations are there? Like, can we ever, like, answer this question? Like, if I give you two ZX diagrams, when are they equal? So there is a nice set of rewrite rules, and this is all you need. There is one more rule beyond this, but it's not that important. In today's talk, we won't need it. But this is all you need to answer this question. Like whenever two ZX diagrams are equal, you can prove that they are equal using these rewrite rules. Let's just quickly go through them. The first one is the spider fusion, where you have two spiders of the same color connected by a wire. Then you can fuse them and add their phases. The second one is the identity removal, which I mentioned in the last slide. And the third one is Hadamard cancellation, which I also mentioned before. So those are like fusion rules that don't involve multiple colors. So now start interaction between these colors. So when you have a green spider connected to a red spider in this way, you can simply get rid of this red spider and copy it to all its outputs. It's called the state copy. It's called a state because this green spider with a single output is a state. Okay. Similarly, if you have a pi spider, you can push it through this and copy it to all the copies and just flip the phase here. It's like how when z goes through x, you get minus xz. So this is like a generalization of that in some sense. And color changes when Hadamard changes x to z or z to x. It's the generalization of that. I don't have a very intuitive picture of these two rules, but take my word for it, like these are true statements. When you have like two red spiders connected to two green spiders in a 2-to-2 fashion, you can replace them with one green and one red spider in this way. And whenever a green and red spider are connected by two lines, you can just chop them off. And finally, any ZX diagram that has no inputs or outputs is a scalar. These are some of the scalars that you might encounter. So that's a, yeah. This one here. Oh, this one is a projector. Yeah. Like a +0 kind of thing. Yeah. Yes. Yeah. Clifford? No, this can be any arbitrary linear map between qubits. Doesn't have to be Clifford. Because these phases can be anything. Yeah. Any linear map between qubits you can represent as a ZX diagram, as long as you allow for arbitrary phases. If you restrict these phases to be like multiples of pi/2 or something, that's called a Clifford fragment. Then then it doesn't matter. Like you can just move it anywhere you want. Yeah. Yes. In general, I don't know. I'm sure people are working on this, but I'm not familiar. Yeah. Good question. Actually, yeah, there is a canonical form. Okay, I don't remember the rewrite, but I know that there is a canonical form. Like that's how you, that's what you use to show this, that these rewrite rules are enough and all that, yeah. Okay, now that we are experts on ZX calculus, let's use that to do some non-invertible symmetries. So the first one, let's just do some like warm up with invertible symmetries. So back to the icing model. We have this Z2 symmetry, which is a product of X, which has a ZX diagram can be written this way. And it's cumbersome to write all these diagrams with all these dots all the time. So I use this box notation. It's like, it represents a unit cell, which is repeated periodically in the spatial direction. So this is the ZX diagram for eta. And you can easily check that it squares to 1 using ZX calculus. This feels like an overkill for this problem, but just to get used to it. And the translation can be represented by this ZX diagram, or in a nice notation, it's like this. For L equal to 3, you can check that this is indeed a translation operator. Like, the T to the L is 1. You can check that like this. I colored the wires using different colors just to see that you can, just to make it easy to see that this is indeed the identity operator. But yeah, the colors don't mean anything. As I had advertised before, this is the ZX diagram for the non-invertible or the Kramer's one-year duality operator. And I want to motivate this in the next slide. So the current understanding of Kramer's one-year duality is that it's basically gauging the Z2 symmetry. And Apu told us how to gauge a Z2 symmetry on the lattice. We introduced some qubits on the links, which I use hat to label them. And we meanwhile couple them to the matter fields and then impose Gauss law, do the gauge fixing, at the end of which you get this gauge Hamilton. Now, all this process can be packaged into a single map, a linear map, which is represented by this diagram here, which I converted it into a ZX diagram, but people have discovered this before me. And this is a ZX diagram that does this. So this is a gauging map that takes the original system on the sides, but the output is a Hamiltonian that lives on the links because the gauge fields were introduced on the links. So that's the one subtlety. But what we are interested in is a symmetry operator that acts on the sides. It should be an operator, not a map. To correct for this, we composed this gauging map with a half translation that takes you from links back to the sides. Okay? And the end result is this Hamiltonian with 1 over h instead of h. Okay? So that half translation is this bend here from the links to the sides. So the links are labeled by these half integers. So, okay, now that we understand what this operator is, let's do some algebra with it. We want to check whether it implements the Kramer's one-year duality, and you can verify it like this. If you take the action of D on X is represented by this red pi. You push it through this using ZX calculus, you can work out that it indeed maps it to product of Z on the neighboring sides. More generally, if you take a string of X, it's mapped to product of Z on the boundary of this string. This is the lattice analog of this continuum picture. I'm sure many people have seen this in the continuum, where you have two disorder operators in, like, say, Ising CFT, and you take the duality line and sweep it across this. You end up with disorder operators connected by a Z2 line. This is simply the lattice analog of that. Next, we can compute the fusion rule. Yeah. These dots mean that, like, I have like periodic boundary conditions and closures. Yeah. So in particular, if you take the product of X on all the sides, you end up with trivial, like there won't be anything on the right-hand side. So that's the fusion rule that D times eta is just D. Okay, next, I want to look at the fusion rule of D with itself. So one thing we can already see from the diagram here. So what I did here is compose D with itself, just put them both together. And I shifted this part of the diagram up so that this wire becomes horizontal. This I can do is just a topological move in the ZX diagram. It doesn't change anything about this operator. But what I get then is this small twist turns into this big twist. And you should recognize that as the translation symmetry operator. So we already get the factor of t from this. Now you can evaluate the rest of the diagram using ZX calculus. I don't want to go through all the details, but the end result is that you end up with 1 plus eta. And it's just like 3 or 4 lines proof using this diagrammatics. But if you want to use the operator representation that I showed before, the sequential circuit, it's insane. Here it's so easily, you get it so easily. So here's the summary of the symmetry operator algebra. You have the Z2 symmetry that squares to 1, translation, and you have the duality operator, and I explained how you get this fusion rule. And it's manifestly invariant under translations, and it squares to translation times 1 plus eta. We got everything without ever involving Majoranas. Any questions? Yeah. There is a way to see that, but I mean, I would say that this itself tells you that in some sense. Like D just absorbs eta. It's as if D has 1 plus eta in it. But there is a way to massage it so that you can see the projector. Like there is a way to like deform and like transform this ZX diagram into the sequential circuit times the projector kind of form. So you can go from here to there. Yeah. The diagram I drew is not a projector, right? It's the D, but you can deform it into a sequential quantum circuit times the projector. You can deform it that way. Yeah. Any other question? Okay. So next I want to talk about, I want to generalize this to 3 plus 1D, the Wigner duality. So here, nice Hamiltonian to keep in mind is the lattice Z2 gauge theory. I have a 3D cubic lattice with qubits on the links. And here's the Hamiltonian. I have a Plaquette term. It's like a magnetic flux kind of term. And electric field term is simply X on all the links. And I impose Gauss law, which is the product of X on all the links around the site. Or you can impose it energetically. It's up to you. But, yeah. This model again has some standard symmetries that everyone should know. Like there's a Z to 1 form symmetry generated by these operators. So the product of X on all the links that pairs a dual surface. That's a 1 form symmetry. And it also is invariant under translations and rotations. Now this model is not exactly solvable. We don't know how to solve it, but people have done numerics and we understand the phase diagram. So when H is small, the Z to 1 form symmetry is spontaneously broken. There is perimeter law for the Wilson loops. And when H is large, the Z to 1 form symmetry is preserved and the Wilson loops have a area law. And once again, the transition happens exactly at H equal to 1. This also was understood before this model was analyzed. This is because of the Wigner duality. In this case, it exchanges the 2 terms in the Hamiltonian again. X and Z both get exchanged. So the transition point is self-dual, and once again, there is a non-invertible symmetry at this point. And this was analyzed in the last 5 years or so in the continuum and on the Euclidean lattice. So we can play the same game again. We can think of Wigner duality as gauging the Z to 1 form symmetry. And people have written down maps that implement this gauge. That's numerics, we don't know. Not in Z2. If you go to Zn and n is large enough, then there is a some gapless window kind of thing. I'll come to that some later. Yes. Sorry. That's in 2 plus 1D. This is in 3 plus 1D. In 3 plus 1D, it maps it back to itself. It maps lattice gauge theory to itself. Yeah. Yeah, there is a non-invertible symmetry. I'll talk about it. Yeah, I'll talk about that towards the end. Yeah, yeah. It doesn't matter. Like you can impose the Gauss law energetically, or you can impose it exactly. It's there, microscopical. Yeah, yeah. Yeah, because it commutes with the Gauss law operator. Yeah. You could ask whether it's topological or not. It's not topological if you impose it energetically, but it becomes topological in the constrained Hilbert space. Okay, so in this case, the gauging map is implemented by some circuit like this. I don't want to explain all the details, but you can at least notice that the inputs are on the links. That's where the original gauge fields are living. And the gauge field for the Z to 1 form symmetry should be like a 2-form gauge field, which should live on the plackets. And that's where the outputs are on these 3 plackets here. Okay, so that's the gauging map. But once again, this is a map, not an operator. You have to compensate that by acting by a half translation in the half direction. And that way you get an operator that commutes with this Hamilton. And this half translation, when you square that, you get a full translation in the 1-1-1 direction. You could ask, why is it 1-1-1 and not -1, -1, -1? This is just a choice. There are other duality operators associated with the other direction. Yeah, this is just a choice. I don't want to go through all the details of the how you compute this algebra, but here's the summary. You have the Z to 1 form symmetry that squares to 1, and the duality operator just absorbs it, just like in 1 + 1D. And the duality operator squares to this translation in the 1-1-1 direction times some C, the condensation operator, which has this expression. It is very nice. I want to say a couple of things about this. It's the lattice analog of this continuum result, where the condensation operator is given by this. So in the continuum, this M here is a 3-manifold. In our case, it's the torus, 3 torus, which is just a spatial cubic lattice. And the sum here is over all the 2 cycles in this 3-manifold. And that's exactly what we have. Like we have sum over all these dual surfaces in the lattice. And the denominator here is like gauge redundancy. And that's exactly this factor of 2 to the V. You can even, in fact, rewrite it in this form, where you separate all the Gauss law projectors. And in the constrained Hilbert space, where these projectors are just 1, this remaining expression is exactly this, including the factor of half. They all match perfectly. It's precisely the lattice analog of the continuum middle. Okay. Oh, this wasn't started. 15 more, okay. Oh, sorry, I didn't mention them. Eta xy is the 1 form symmetry operator in the xy plane, the non-contractible cycle in the xy direction. Similarly, eta yz and eta z. Oh, it doesn't matter. Because of this Gauss law projectors, it doesn't matter where you put it. It can be anywhere. Like if you want to shift this, you just bring in appropriate factors of these Gauss law operators into this, and yeah. Oh, that was here. Here, this. The product of z's on all the links that pierce this dual surface. Any other questions? So now, yeah. I'll come to that. Yeah, that's the low energy consequences. Yeah, I'll definitely come to that. So you can generalize this further, like much way beyond like the examples that I talked about before to LDPC codes. So the input here is like a bipartite graph where you have some vertices on which the qubits live. And you have, so there is a left vertex set and there is a right vertex set associated with the interactions. And in the quantum information literature, they're called checks. And given such a bipartite graph, you can write down a Hamiltonian of this type, where this B here is the product of all Z. So for each vertex here, I take the product of all Z that are adjacent to this vertex. That's like a stabilizer term that you add to this Hamiltonian. The second term is simply a transverse field term. And when people talk about LDPC codes, typically you don't have the second term. You have only this one, the first term. So it's a classical LDPC code. But you could add this term without affecting anything. And this model has, again, a Z2 symmetry that's generated by product of x's, a particular set of x's, where this A is in the kernel of this matrix sigma. Now, okay, I didn't mention that, but sigma is this matrix, bi-adjacency matrix. What that means is it's 1 when there is an edge between V hat and V, and it's 0 when there is no edge. That's all it means. If this feels too abstract, here's the Ising model example, where the black vertices correspond to the sides of the lattice. The white vertices correspond to the links or the interaction, the two-body interaction term. And this is the bi-adjacency matrix in this case. And the kernel is generated by just all ones vector. And that is precisely the product of all x operator that we saw before. Okay. Now you could ask, what are the spatial symmetries and where do we get these non-invertible symmetries? And that's where the automorphisms of this graph enter. Very simply, automorphisms are like a one-to-one map between the vertex sets that preserves the edge structure. That's it. And in the case of a bipartite graph, you have two kinds of automorphism. Preserving automorphisms, which preserve the left set and the right set, and reversing automorphisms that exchange these two sets. And it's these preserving automorphisms that give rise to spatial symmetries. And as I'll show later, the reversing ones give rise to non-invertible symmetry. Just to give an example, in the case of Ising model, you have this kind of a preserving automorphism that maps black vertex to the next black vertex. That's like a one unit translation. So this is the translation symmetry. And there is a half translation that maps a black vertex to the neighboring white vertex. This is a half translation. And this corresponds to the Kramer-Swania duality operator, as I'll show. So in this case, the gauging map can be written very easily. In fact, once you know what the bipartite graph is, the gauging map is basically take that graph, replace all the left vertices with green spiders, right vertices with red spiders, and add some Hadamards, and that's it. That's the gauging map. In this case, it's very simple. Now that you have this gauging map, you can work out the algebras and all that. But as I said, this is still a gauging map. We want to convert this into an operator, and this is where the reversing automorphism helps. What this map does is take something, a Hilbert space on the vertices in V, and gives you a Hilbert space on the vertices in V hat, in the right set. To change it back, you compose it with a reversing automorphism that takes you back to V. So for every reversing automorphism, you get a duality operator given by this expression here. And now you can use ZX calculus again and derive all the algebra. And this D row implements the Kramer's or the duality symmetry. It exchanges the two terms in the Hamiltonian according to this reversing automorphism. And you can also work out the fusion rules. And the most interesting one is this, the duality fusion rule, where if you take two duality operators associated with rho and rho prime, on the right-hand side, we get a preserving automorphism. It's like a spatial symmetry associated with this preserving automorphism. Basically, when you apply two reversing automorphisms, you end up with it's like equivalent to a preserving automorphism because you're back to the original vertex. You can do this on any graph. Yeah, any bipartite graph. Yeah. And this part here is like the condensation operator. It's sum of all the Z2 symmetry. It's the analog of condensation operator. And this also gives us some nice condition for when this duality operator mixes with spatial symmetries. In particular, if rho prime is equal to rho, and you want to look at this fusion rule, you get T rho squared here. And if rho is an involution, meaning I'll give an example soon. If it squares to 1, then it does not mix with the translation, with spatial symmetry. So for example, in the case of Ising model, the half translation is a reversing automorphism, but it's not an involution because if you do it twice, you get a full translation, and that's not identity. But there is another reversing automorphism, which is like a reflection about this red line here. This is also a reversing automorphism because it exchanges the black and white vertices. But when you apply it twice, you go back to the original graph, original labeling of the graph. So this is a reversing involution. And the duality operator associated with this is it does not mix with any translation or other spatial symmetry. There are more examples that you can explore. Basically, like given any LDPC code, you can ask this question and you can work out all this stuff. Okay. So yeah, finally I want to talk, yeah. like icing times, 2 copies of icing, one on the sides, one on the links, is just a swap, and that becomes a non-invertible symmetry. So yeah, that doesn't mix with translation. Yeah. Any other questions? Yeah. Yeah. Okay. So let's do some physics now with all this technology. So one of the aims of uh, a quantum many-body problem is to determine the low energy spectrum. So there are 3 possibilities. The first one is like the ground state could be non-degenerate and there is a gap. So it could be trivially gap, or it could be part of a gapless band. Gap. It could be gapless, or there could be some non-trivial degeneracy within the ground states, and there is a gap. These are some 3 possibilities that you can have at low energies. But in some cases, when you have a duality symmetry, the trivially gap phase is not alone. I'll soon discuss some examples of this. And the other 2 options are all realized in some models. Okay. Yeah. This one. It's just some band, like there are so many states here, lots of states. Huh? Here? I mean, there could be some gap above some band, like, I don't know, like the spectrum could have some gaps randomly somewhere, we don't know, right? Like this, for example, can happen in like semiconductor or metal or something. Yeah, in a gapless system, there could be some band, and then there could be some gap and some bunch of other states, and then there's some other band. Yeah. But all I'm interested in is on only this low energy spectrum. So I don't care about what happens everywhere else here. Yeah. Yeah. Okay, so in 1 plus 1D, this statement is true. When you have Kramer's 1A duality symmetry, you cannot have, it's not compatible with a trivially gap phase. So the possibilities are either gapless, which is realized in the 2nd order transition in the icing model, or it could be gap with spontaneously broken duality symmetry. And in this particular case, the ground state degeneracy is always a multiple of 3. With this eta, you mean? Yeah, without eta, Kramer's 1A cannot exist. Yeah. So the argument, like basically, so essentially the argument is like you have this fusion algebra, right? Like the Tambara Yamagami with Kramer's 1A and C2 symmetry. You classify its representations, and all its representations are like multiples of 3. There is no trivial representation for this algebra. It becomes a representation theory question, and there are no trivial like one-dimensional representations for this algebra. That's a math result. Yeah, I don't know how that was proven, but yeah. If you ask me, that's a bit subtle. I'm not entirely sure how this can be proven, but Levin has some rigorous arguments for this. I'm not familiar with the argument, but yeah, this is the result. Yeah, I can tell you why a trivially gap phase is excluded. That I know. There is a simple physical explanation for that. Basically, if there is such a phase, it must be some SPT of the Z2 symmetry. But there is no non-trivial SPT of Z2 symmetry that's invariant under gauging the Z2. That's it. Yeah. But I don't know how to argue that it must be a multiple of 3. That's some math result. So you might wonder like if there is a nice Hamiltonian that realizes this latter possibility, and indeed there is. You can start with the icing model at the critical point and deform it, where the deformation is given by this. And for large enough lambda, this model becomes gapped, and it has exactly 3 ground states. Basically, it's like the first order transition between these ferromagnet and paramagnet. So you get 2 states from here one state from here, and they coexist there. That's the threefold degeneracy. Okay, and in fact, there is a nice particular point in this Hamiltonian at lambda equal to half and h equal to 1, where this model becomes frustration free. And its ground states are precisely this all zero, all ones, and all plus state. Now, this all zero and all one are the ground states at this point here, h equal to 0. And all plus state is the ground state at h equal to infinity point. And we see that these are precisely the ground states of this Hamiltonian at some point here, like where lambda equal to half or something. And this is very nice because now you can explicitly see what the representation of the symmetry. This is the three-dimensional representation, and this is how the symmetries are. Like eta exchanges these two states and preserves this state. On the other hand, D maps both the 0 state and the 1 state to the plus state, and it maps plus state to like 0 plus 1, like an equal weight superposition of 0 and 1. So that's the algebra. That's a representation of this algebra in the ground state. This is nice. Can move on to 3 plus 1D. Once again, you can argue that if you have Wegner duality and the Z2 1-form symmetry, it cannot be trivially gapped. The argument is again the same. There is no SPT that's invariant under gauging the Z2 1-form symmetry. So this is not possible. But gapless and gapped are possible, gapped with degeneracy. And the gapless case is realized in the Maxwell theory at a particular value of coupling. And now, because we are in higher dimension, there are like two possibilities for gap. Either the Wegner duality symmetry is spontaneously broken, which is what happens at this first order transition point in the lattice gauge theory. Or it could be preserved. For example, there could be a TQFT that's invariant under Wegner duality. I think this is almost excluded in this paper, but I think there is still some caveats here, so I'm not sure. I think it's still open. It's still not settled. But okay. What I want to discuss next is a deformation of this model of this lattice gauge theory, similar to the one in the previous slide, because we don't know how to solve this model. Like we believe this is first order based on numerics, but it'd be nice if you have a concrete Hamiltonian where we can realize this explicitly. That's what I want to talk about quickly. Here? No, we don't know. I think it could be even 2. Yeah, because there are Z2 1-form SPTs that there are like 4 Z2 1-form SPTs, and 2 of them are exchanged by the gauging of 1-form. So if you have a direct sum of those 2, that's invariant under gauging, and it's like just 2 ground states. So, yeah, you can even have 2 there. So 3 plus 1D Maxwell theory at this particular coupling, at a particular value of E squared, it has Wegner duality symmetry. Basically, you gauge it, you change the coupling value, but then you use electromagnetic duality to come back to the original coupling. And this works exactly at one particular value of coupling, and that's given by this. In terms of E, it's like E square equal to half or 2 or something like that. Oh, no, not in this, not in this. It's just in 3 plus 1D Maxwell theory. It's not realized in this phase diagram, or maybe somewhere else in the phase diagram, but certainly not here. Okay, I didn't mean that this thing is realized here. It's not. This first order corresponds to this D being spontaneously broken. Yeah, but there might be some kind of deformation where you end up with 3 plus 1D Maxwell. I don't know. There could be. Okay, but the deformation I want to talk about is this one, where you recognize the lattice gauge theory in the first 2 terms. The deformation is this one, where for every pair of link and placket that meet orthogonally at a vertex, I write the product of Z around the placket and X on that link. I add every such term to this Hamiltonian and with this coefficient. It preserves the 1-form symmetry and also the Wegner duality. Basically, if you apply Wegner duality symmetry on this term, you get a slightly different term, which is also included in this sum. So this sum preserves the Wegner duality symmetry. So this Hamiltonian is invariant under that. Once again, when h equal to 1 and lambda is equal to 1, this model can be written as a sum of projectors, but it's not a commuting projector model. In fact, it's frustration free. You can compute the ground states exactly. They're given by the toric code ground states, which are the ground states of this term, and a trivial product state, which is a ground state of this X term. And these are the only ground states. There are no other ground states. This can be proven. In fact, quite remarkably, we can show that this model is gapped. Despite this being not a commuting projector model, we can show that this model is gapped. It's quite interesting. What all of this means is D is spontaneously broken. So D exchanges the toric code states and the product state. And because this Hamiltonian is gapped, it's like spontaneously broken. One can play the same trick for LDPC codes. You can define a deformation, again, find the same features, but in this case, the toric code states are replaced by the code space of the LDPC code. So you have a coexistence of the code space and the product state. And we can prove that this model is gapped. This is not a commuting projector model defined for any arbitrary bipartite graph, and we can still show that it's gapped. Okay. And in general, LDPC codes need not have duality symmetries. They have them only if they have reversing automorphisms. But whenever such symmetry exists, the deformation also preserves that, and that symmetry is spontaneously broken. Okay. I don't know how much time. Okay. I just wanted to say just 2 minutes, a couple of things about what possible phase diagrams these models can have. Here's the phase diagram for, let's say, the 3+1D lattice Z2 gauge theory that I was discussing. Numerics tell us that on this line, there is a first order transition. And when you add the deformation, this transition must exist like this. Or it might close somewhere here, I'm not sure, but this is just a schematic diagram. But what okay, one more thing is this line has to be vertical exactly at h equal to 1 in the case of Z2 gauge theory because of the self-duality, but in general for LDPC codes, it need not be. It could bend this way or that way, like, I'm not sure. This is just a schematic sketch. But what I want to emphasize is there is this frustration-free point where we know these two phases coexist and it's gapped. So this must also be a first order transition. It's reasonable to believe that the entire thing here is like first order. And numerics tells us that even in these models, there is a first order transition here. So this is the kind of phase diagram you might expect. Slightly more interesting is 1+1D Ising model, where we know this transition here is second order, but the frustration free point is still first order. So there must be a tricritical point along this transition line. And indeed, in the case of Ising model, this tricritical point is described by the tricritical Ising model, Ising CFT. But a new prediction is, even in 2+1D Ising model, we know that this is a second order transition described by 3D Ising CFT. And then there must be a new tricritical point here in this phase diagram. And I don't know what the CFT that describes this point is. And yeah, that's a new prediction. And finally, you can generalize all of this story to Zn. And for large enough n, there could be some gapless windows here between the two gap phases. But again, I know that this frustration free point is like a direct first order transition, so this gapless window must close. And that leads to some kind of a bifurcation point. So these are some kind of phase diagrams that you can predict just by knowing that this frustration free point is like first order and gap. Okay, that's all. It's just a quick summary of whatever I talked about, but yeah. Thank you.
Questions?
This one. For example, in the 1+1D Zn clock model, it could be 1+1D or 3+1D, like in both. In 3+1D Zn gauge theory, so you have topological Zn gauge theory here, topological order, trivial phase, and this is described by U1 Maxwell theory. Yeah, okay. In that case, this line should be vertical at h equal to 1, but there is still, so this self-dual line goes through this gapless window. And this bifurcation point must be along that self-dual line. Yeah. Yeah, these two lines must be related by self-duality. Yeah. Yeah. Yeah, it should be somewhere here, wherever the self-dual line ends, at h equal to 1 and lambda equal to 0. That's the Maxwell theory at tau equal to 2i. Yeah.
I was just curious, how do you prove that it's gapped, like the frustration between?
Oh, very non-trivial. We can discuss later. I can't explain it now. Oh. I think it's all numerics. In the 1+1D ZN clock model case, there is like analysis done by these people, Jose Cardanoff and Kirkpatrick and Nelson. Like you take the C equal to 1 compact boson and turn on like operators that preserve only Zn subgroup of the U1 symmetry, and you can analyze like the RG flow and all that. Then you get this phase diagram here. I don't know if there is a equivalent analysis in 3+1D, starting with Maxwell and like turning on, like what would you turn on? Like the charged operators are Wilson lines. So I don't know how to exactly do this. Or maybe you can, you can couple the charge and matter and then analyze what it flows to. And I think you can analyze this in field theory, this phase diagram, but I think it was also, it's like, this was observed numerically first, even. No, this one here has 9 ground state. On a sphere, yeah. Like I basically have like topological order plus trivial. They're just one state on a sphere. So. The SPT thing was also 2, yeah. Yes.
If there are no other questions, let's thank the speaker.